All right, we are picking up today with lesson 4.5, and we're going to talk about scatter plots and lines of fit. Scatter plot should be old information to you because we have dealt with those in pre-algebra before. Lines of fit, I think, may be a little bit new. So, question?
What's a line of fit?
Well, that's what we're going to talk about. Yes, Aiden?
Scatter plots do not have a slope.
Scatter plots, yeah, we'll talk about that in a minute. Scatter plots don't necessarily have a set slope the way we've been thinking a slope, but our line of fit will have a slope. Harley,
So is a line of fit basically like a best fit line?
pretty
Like
much.
an average.
Yes, line of best fit, sometimes they're called. Sometimes also called trend lines, but we'll talk about those actually in the second part. So today our first objective is to investigate relationships between quantities by using points on a scatter plot. That's the kind of stuff you're used to doing with scatter plots, just plotting the information on a graph and seeing if there's a relationship that shows up once you've plotted the data. And then objective 2, we'll use lines of fit to make and evaluate predictions. So see if we can figure out where to place points on the graph based on how the line shows up on there. This again, scatter plot information is stuff that you should remember, hopefully from pre-algebra. A positive correlation on a scatter plot goes up as we read it from left to right. And as you look at it there, it's kind of small print, but it says as x increases, what does y do? Y increases. So they increase together. That's a positive correlation. A negative correlation, though, it goes down from left to right, so as x increases, what does y do?
Decreases.
It decreases. So that shows a negative correlation. As one goes up, the other one goes down. And then no correlation, there's no relationship to show that, as x increases, there's no way to predict what y is going to do. Is y going to be high? Is y going to be low? We don't know based on the placement of the x. A vocabulary term for you in this lesson is bivariate data. What does that prefix bi mean in front of the word to? So bivariate data is made up of two variables. You can kind of see both those words, two variables, bivariate, right? So that's where that word comes from. Harley?
So bivariate like two variables. So it's two variables used in standard form.
Yeah, the x and the y are our two variables on all the stuff that we've been doing with graphing. So all the things that we've been doing, whether it's any of the forms of equations that we've looked at, have all had to do with two variables. But they don't classify as scatter plots because the data is not scattered on most of the graphs that we've been looking at as we've done linear equations. We're graphing lines, not scattering data on the graph, right? So then the scatter plot is just used to show that relationship between the two quantities. All right, let's look at an example. Determine whether the graph shows a positive, negative, or no correlation. If there is a positive or negative correlation, describe its meaning in this situation. Okay, so Joaquin
It has a positive correlation.
has a positive correlation because as x increases, what does y do? Y increases as well. So the further we move to the right across the graph, the higher we would expect the y value to be. Okay, so specifically related to this graph then, what does a positive correlation mean?
Going up.
Heidi?
The more hours you work, the more money you get.
Yeah, this is a graph having to do with wages. The x value is the number of hours worked, and the wages are the y value there. So the more hours you work at a job, you would expect to make more money, right? As far as the things related to this graph are concerned, that would be true. Okay. I don't have a lot of examples to show you about scatter plots because that's the type of thing you'll do. You'll look at a graph of data, you'll make a decision, is it positive, negative, or no relationship? If it is a positive or a negative relationship, then you have to describe that relationship and what it means in terms of the data that is being graphed. Harley?
But shouldn't the plot up there, shouldn't it be a line?
Not necessarily, because they might not be talking about a specific job, or they might be talking about people who have different years of experience. So some people make a little more per hour than others make, or there are other things to consider besides just one person working a set number of hours, we don't have enough information to be able to judge exactly what this graph is about. But in general terms, the more hours you work, the more money you'll make. Harley.
How much money would a person make per hour?
Well, I'll tell you what, we're gonna look at that here in just a second, okay? We're gonna look at that on the next graph. So, if a scatter plot shows a relationship in the data, a line of fit can be used to describe the trend in the data. All right? And if you look on the next slide, we'll kind of talk through this next slide as we do some things with that graph here in just a second. We'll go back to that graph. But on this slide, to make a line of fit, first you have to make a scatter plot. You have to be able to see a visual image of where the data lies on the graph in order to make your line of fit. Then step 2 is kind of the interpretive part of it. You have to make a line or draw a line that seems to pass close to most of the data points. It's not an exact science, okay? It's called a line of fit, a line of best fit. You just kind of make a judgment about where the line goes. Step 3 is use 2 points on the line to fit to write an equation for the line. One thing I'll say about that is you want to use, it's best to use points on the line that are close to the ends of the line rather than 2 points right from the middle of the line. If you use points from the ends of the line, you'll get a better spread of the data and a more accurate reflection of the proper equation for the line. And the other thing I'll say about that is your line may be a little bit different than mine. The points I choose may be a little bit different than the points you choose. And so your equation might look a little bit different than my equation looks, right? And that's where we always, in my experience, that's where I always run into trouble in classes is when there's like things that are open to interpretation. You guys kind of panic a little bit because you want me to tell you the right answer, but your answer might be a little bit different than mine, and it's okay. So you need to be comfortable kind of fitting things on there as the way they look best to you, and then be ready to defend why you put it there. Okay? And then step 4, we'll use the line of fit to make predictions, and that's what Harley was asking a second ago about, how much would somebody make who worked more hours or something like that. So let's go back to this line, and we're going to find a line that kind of fits the data. First of all, this is a special type of graph if we're going to graph a line, because what's one point that should be really, really obvious, Bryson?
It'll go through the origin.
Why is it going to go through the origin?
Because if you work 0 hours, you're gonna get $0.
That makes sense, doesn't it? I don't know many bosses that will pay you, $10 for not showing up, but maybe some will. Not been my experience. Okay, so we know it's going to go through the origin, so we'll start here, and then we want it to make a best representation of the data. And so we want to have about the equal number of dots on each side of the line, and we want it to pass about equal distance from the line and all of those things. This one, there was a specific point that really helped me draw this line of fit. That point right there seemed to fall right on the best line, didn't it? Okay, and I could have moved that line a little bit, one direction or the other. I mean, I don't know if it'll let me move it or not. A little bit one direction or the other would have been, oops, but we don't want a line that looks like that, do we?
No.
And we don't want a line that looks more like this. Okay, so a line that gets as much of the data as close to it as possible is where we want that line to be. And now that I have one point that really is on that line really well, that's the point that I can use to help me write an equation. And so in order to write a slope-intercept equation, what 2 things do I need? I need a slope and I need a y-intercept. Y-intercept's really easy on this one. What's y-intercept? 0. Okay, so all I need to do is figure out the slope. What kind of graph is this? Since it goes through the origin, it is a direct variation. Direct variation equation looks like y equals kx. Do you remember how to find the k value? K equals y. How would we solve for k here? What would I have to do to get k by itself?
Y over x.
K is y over x. Whoops, y over x. So if I have an ordered pair, I have a y and an x that I can use to write my equation or to find my k value. Do I have an ordered pair?
Yes.
Yep.
I have a really good ordered pair that's right on the line. So what is that ordered pair?
400.
Oh, please
Oh,
give it to me in
32.
proper order.
32.
32400 is the ordered pair. And so since k equals y over, over x, that would be 400 over 32, right? So what's 400 over 32? Just divide it. Comes out nice and neat.
Hold it up.
12 and a half? Oh yeah, okay, 12 and a half. I was thinking ahead, I was thinking of another number. 12 and a half. And so my equation then would just be y equals 12.5x. And so in general terms, for this graph, if I wanted to figure out what somebody might make if they worked 50 hours, I would just put y equals 12.5 times 50. 625.
I think so.
Y equals $625. And so even though that doesn't fit on the graph, we could still solve for it based on the equation that we wrote.
That's still an estimate, though.
It's still an estimate. We're going to be close, but it could be $600. It could be $650. But that still gives us an estimate of where it would be.
If we were, we would make an exact line, would we average all the numbers together? Like to make an exact.
If you wanted to make an exact line, and you knew, in this case, since we know what the y-intercept is for sure, you could actually, I suppose, average all the slopes and find an exact line of fit, but man, that would be very labor intensive. So this one is a very good estimate and one that we can use and make reasonable predictions, so we'll go with it. All right, Harley?
So is it possible for like a scatter plot like that to have a equation that works for all the points?
When you get into things like calculus later on, you'll be able to write equations that are more specific than this, and will give you a little better representation of the data. But I don't know of a way to write one that represents every possible dot on a scatter plot like this. That would be math that's over my head if it exists. Tessa,
So what do we write for like the slope of
what is the slope? Slope in a direct variation, slope is the same thing as in our y-intercept. Our slope-intercept is m. So k and m are the same thing, right? So k is the slope, m is the slope. Same thing. Most of the ones, well, I think the ones for the most part that we'll do today will not be direct variation. So you won't be able to use the direct variation shortcut. You'll have to actually write a slope-intercept equation, such as this one. So the table shows the largest vertical drop of 9 roller coasters in the United States in the number of years after 1988 that they were opened. Identify the independent and dependent variables. All right, so what's the independent variable and the dependent variable in this graph?
independent is
Independent is
like years since,
years since.
and dependent is like vertical.
Dependent is vertical drop. So independent is always the x, and dependent is always the y. All right. Is there a relationship in the data?
Yes.
When you look at the graph, you see what type of relationship. It's a positive relationship. So as the number of years increase, the drops increase as well. Let's predict the vertical drop on a roller coaster built 30 years after 88. In order to do that, we have to have an equation because the graph isn't big enough for us to stick a dot on there for 30 years after. So we've got to write an equation for this. So we need to pick out 2 points. 1 point is really, really easy to see that we could use. Okay, so we can use the point 12 what?
300.
12, 300. And we can use,
A 0, 1,
0.
40.
0,
20.
1, 30.
okay, that one's a little bit harder to see. You know what we could use? And this, again, this is open to interpretation. You can choose to use the y-intercept if you think you can estimate that. It goes really close to this point right here, doesn't it? So that's a really good point for us to use. Let's use 150,
Well, one is
mainly because that's the one I used as I worked this problem earlier. Yes?
Or would that be a 1, 1?
Yeah, it's
This is a 2, isn't it?
Yeah,
no,
so
it's a 1.
2, 1, right here.
Well, which one are you?
I'm right there on the 2 and 150. It's really close to that. The line doesn't go exactly through that point, but it's really close to it, right? That's going to be good enough. I know this is usually in math, I'm telling you, be as exactly precise as you can be, but this is one time when we're going to estimate. We're going to get it close, okay? And so the first thing I need to do is find a slope.
Slope is
150 minus 300.
Let's keep it positive. Let's do 300 minus 150 over
12 minus
12 minus 2. So 300 minus 150 would be 150 over 10, which is 15. So 15 is the slope. Now I just need to write an equation in slope-intercept form. So I've got a slope, I've got a point that is on the line. Okay, so let's use point-slope form.
300.
Y minus 300 equals 15 times x minus 12. All right, so y minus 300 equals 15x minus 180. Add 300. So y equals 15x
minus 1.
plus 120. All right, before we go any further, let's talk about this equation. What are the parts of this equation? What do they mean?
120
It
is
goes
the
up.
y
It
intercept.
goes up 15, it goes 15 feet in the drop each year.
Okay, so the drop increases 15 feet every year. That's what the slope means. So every year since 1988, the next biggest roller coaster that was built had about a 15-foot more drop, right? Okay, what does this 120 mean?
It means it started at 120.
Okay, so in 1988, 0 years since 1988, so that would be 1988, the tallest roller coaster had about a 120-foot drop, okay? All right, now the question, we wrote this equation in order to answer a question, and the question is, predict the vertical drop in a roller coaster built 30 years after 88.
Well, we have a
y
we need a y.
equals 15 in parentheses 30 plus 120.
Yep, put 30 in for x because it's a year, it's the independent variable, plus 120, oops, 120. And so y equals 450 plus 120. So what does that mean?
That means it's 570 feet.
Okay.
The year, 30 years later.
What year would that be?
2008.
2018. So like in the next year or two, if they're building roller coasters somewhere, it'd be interesting to find out if any new roller coasters being built are anywhere near 570-foot drop.
That would be
I have no idea. I don't know if that's true or not.
Field trip.
Field trip. I like it. Field trip. Let's do it. Okay. Here is your assignment. It's only 9 questions, but some of these can get a little bit long and tedious. You will have to do some graphing of scatter plots. I suggest you make your scatter plots not super tiny. Don't make them huge like full page, but make them reasonable size so that you can kind of spread them out and get better representation of the data. We will spend time on this in class tomorrow, so don't freak out if you're having trouble with it. We will spend time making scatter plots tomorrow.
Can you record the whole class?